everyone. My name is Xiaoliang, and I'm from the University of Edinburgh, and I am supervised by Ajitha, Rajan, and Peter Bell. Today I'm going to show you the work in the previous year. As you can see from the title, can we trust explainable AI method on ASR? This is actually, you can see from here, is based on a previous work from us, the explainable AI method on ASR. So the first thing I need to say is to say something, background knowledge from the previous work, like what is an explanation effective for the ASR and why we need that. So actually the ASR is always, the deep learning model, the black box model, so the black box nature makes it very hard for our human to understand. That's the reason why we need that, but we can see, other motivations from this very simple example, like this figure. Like, let's imagine a scenario. There is an English learner, and I want to say, can you see 3 birds? But the ASR will transcribe that into 3 birds. There is one small mistake, but the meaning is different. So here we want a kind of explanation to tell the learner, like which part of the waveform will cause this kind of figure. And we can see here the explanation will be this is pronounced wrongly. So for the English learner, this explanation will help him to improve the pronunciation. And for the same kind of the same example will also help the developers to debug. And next is the definition of that on the ASR. As we all know, this kind of explanation always exists in the image classification task and the NLP task. Like when an image is classified as a dog, maybe the explanation will be the important scores for the pixels from for all pixels in this image. And finally, we may get like those pixels around the dog's eyes, dog's nose may have higher importance scores. So for us, we have the same definition. The explanation should be, the importance rank of the frames in audio. And like this example, the mistake files can be explained to those important frames in audio. But here is still, a big challenge. This challenge still exists in a lot of explanation works, like the length of the ground truth. This is because we can generate explanations, but it's very hard for us to have a kind of ground truth to say, oh, this kind of explanation is right or wrong, or to what extent is wrong. So we start to find a solution for this kind of challenge. We focus our attention on the timid phoneme recognition task. Actually, there are 2 reasons. The first reason is because the timid dataset always has a ground truth label, labeled especially labeled by the experts. The second reason is about as we all know, for the ASR transcription, the whole sentence, for the different words, the words can be affected by, distant words, which can be called, long span problem, which makes it very hard for us to find a ground truth. But for the phoneme recognition system, the phoneme is always affected just by the nearby phonemes or itself, which means it is very simple or controllable, easy for us to evaluate. The next is the method. The first is still the definition. The definition is same like before. Should be the important strength of the frames in audio. But for the method, we have three. The first is a very classic one, the line, and second one is MTS and Lamial WS. They are all proposed by us to fit it more into the speech domain. And we can see from here this figure. In the left part is an original audio divided into 6 segments, and there are the output transcriptions. The first step, we will do some preparation on the original audio by mask the segments randomly. And you can see from the right part, there are some mutates. And for every mutate, there is the black part is the segments being masked, and there are the transcription. After this step, those transcription and the mutates will be fed into the explainable, very simple explainable model, the line WS and line TS. And after this step, the segment ranking will be generated. The next thing, I will explain the line with a very simple example, the linear regression. You can see from here the formula, and let's go back to the previous slide. For every mutate in the right part is actually serve as a training point. Let's use the first one as an example. In the first mutate, the first segment is not masked, so the x1 will be 1, the x2 will be 1, 2, the x3 is 0, so it will be 1, 1, 0, 1, 1, 1 for the x1 to x6. And for the chosen phoneme, the transcription is different. So the y is 1. Once the transcription is the same, so the 1 will be 0. So after fitting this very simple process, we will get the weights for every segment. So that is a very simple example. We still can use other simple explainable models like for random forest or logistic forest, logistic regression. Yeah. But after that, we did a little more work based on the line. That is because we noticed that the phoneme is always affected by the nearby phonemes or itself. So we fixed a sliding window around the chosen phoneme, which means we can just do the perturbation inside of this window instead of doing a lot of perturbation outside of this window, far away from the chosen phoneme. Actually, those perturbations are not that useful. And after that, we also noticed one problem is no matter line or line WS, we always use the segments from the timid dataset. But as we all know, those kind of segments not always exist in other datasets. So we use the time segments, which means we just divide the audio into the seamless segments, just using the time steps. That will be easier for us to generalize our method to other datasets. And metrics, I just put one metric on here, but actually we have 7 different metrics in the paper. This matrix is pretty simple. Actually, it's N1. N1 means N means the total number of the phonemes, and N1 is the number of the phonemes with the top ranked segments matching the ground truth. So actually, it's more like the accuracy metric. For the results, as you can see from this figure, the best one is the line TS. But we can see from here the Lime WS, and LMTS, they all much better than the random guess. And we actually notice another interesting thing here is for different gender, different group, the female and the male, they are quite different. They are not that quite different. There is some difference. That is because in the timid data sets, there are more male speakers than female speakers. That is also, I think, a way of use our explanation to find some bias in the training data set. And the Lime TS is the most reliable, and all techniques, significantly better than the random guess. There is an advertisement for myself. I'm looking for a postdoc invitation, and if you are interested in my work and want to expand your research interests, and here is my email, and just contact me. I'm very happy to hear from you.